if transpose. So that's the full finite deformation theory. Let's linearize it. So remember, we already linearized B, and it turns out that it's just 1 over K over Ks, right? That's just a constant, it's a number, right? Therefore, dB dt is going to be equal to 0. Remember, we had that J dot is equal to J times the divergence of V. Let's write out the divergence of V. That's like partial V1, partial X1, plus partial V2, partial X2, plus partial V3, partial X3. Anybody recognize that that is simply dii, where d is the rate of deformation tensor? Right? Remember, d ij is equal to 1/2 partial v I partial xj plus vj partial xi. And then you might remember from your homework assignment that in the small strain limit, D is approximately equal to the small strain, the rate of small strain rate. You know, other approximations in the linearization, like this thing is approximately equal to that thing, right? Which is approximately equal to also just the reference. And again, we're talking about, yeah. And you know, another way, obviously this is equal to J phi. Well, another thing about when you linearize it, J is approximately 1. Right? Because we're talking about small strains, right? And J is like a percentage change in volume. So for small strains, it's hardly any percentage change in volume. Right? But if we don't even need really that, I mean, yeah, well, if we just basically then take these terms and plug them back into the equation above, then we have where again 1 over phi f rho f is equal to w is equal to and I'm going to ignore gravity. Basically what I'm doing is I'm writing down the final equations for polar elasticity that we're going to solve computationally, and we're going to ignore the gravity term just to make things simpler. We'll always just imagine flow in a plane. We just only have so much time in the semester. It's, one less detail. So then ultimately, the final equations that we're going to solve that's the conservation of mass equation coupled to the solid deformation, and then our conservation of momentum equation. And, this is the equilibrium form, so we're ignoring the inertial terms. And, this is exactly what we had before. The linearization comes in through by just using a linear constituent model. So this equation, if you use a linear constituent model, it is a linear equation. So we'll just use a linear constituent model. That is one that uses a stress in terms of the strain, the small strain. Right? So then, what are the unknowns in those equations? We can write stress as a function of strain, and strain as a function of displacement, right? So there's unknown displacements and pressure, right? This is, in 3 dimensions, this is 3 equations, right? So there's 3 unknown displacements. This is a scalar equation. There's unknown pressure. So you have 4 unknowns, U1, U2, U3, and pressure. So you have 4